we covered ball screws and lead screws pretty well, I think. I always think about the things that I forgot to tell you at the end. Like in lead screws, if it's vertical, you're supposed to use a brass nut instead of a Delrin nut, both for strength and for, oddly enough, for vibration and sound. But it's a subtlety. It's not that important. We talked about, yeah, we covered this. So the next thing we have to deal with is the other ways to translate rotary motion into linear. And you have to do this because most motors are easily made to rotate and they're the lowest cost made that way. And so if you have anything but rotary motion, you have to translate it. Lead screws and ball screws are good for short distances generally. And I say generally, I mean, the longest ball screw I've ever done was about 20 feet long, and it was about 6 inches in diameter. It was on a telescope stand on the top of a mountain in Hawaii, just this, vertical, huge ball screw. So they can be very, very large, but in general, they're 1 meter or less, and they're 1/2 inch in diameter, 3/4 inch diameter. Kind of is probably the sweet spot of where most axes are rotary to linear conversion done with ball screws or lead screws. But there's a lot of applications, including the concrete extruder, which have lower accuracy requirements or higher speed requirements. So let's start, the first one, let's start with belt and pulley. I'm going to cover the motor sizing part of things and the motor sizing, how to actually do the calculations. Generally, what we're talking about here is some sort of, and I'm ignoring the bearing structure. So you could have any of those linear bearing structures that we talked about, linear guides or wheels or rollers or ball slides, where you have any of those linear bearing structures could be in play. This is the drive mechanism part of it, how you make it actually translate back and forth. So I'm going to put something like this together, and that's a standard belt and pulley system where we're moving a mass. The whole idea here is that this mass is moving back and forth, and you have some specification of distance and accuracy and speed that you're trying to hit in linear units there. So, and obviously, in order to make that mass move back and forth, if you're going to put a motor on it, you're going to do some sort of motor. And in this case, we would, let's just make this a little bit better here. So you'd say put a motor on this, and then the belt would be behind it, motor. Now, this is pretty tempting to do, but there's a couple of main problems with doing this, just putting a motor on a belt and pulley. First problem, shaft loading. If you're going to put force up here, that force, here's a little motor shaft down in here. If you're going to create force, which is, mass and acceleration, you got to push against something. And the only thing you have to move that mass to push it back and forth again, you got to push. Basically, if you're going to do it that way, you can't push here. You have to pull here, right? So because you can only apply tension, you can't push things around with by pushing on a belt. It's not going to work. It's going to go flimsy. So you've got, the only thing you can do is pull. And if you're going to pull on that, you're going to end up putting a force on the shaft, and you're probably going to quickly overload the bearing that's in the motor. They didn't put a bearing in the motor that is designed to handle side load forces. And so it doesn't take very much if you're calculating out the force. These typical bearings are 15 to 20 pounds of side load at some distance from the motor shaft. So you're pretty much going to rely on motor bearings, and you're gonna limit the life of this machine pretty quickly. So what do you do to solve that? Well, the thing you're pretty much forced to do is kind of, I'll draw this in side load, but you're pretty much forced to either offload this forces onto a set of bearings. So for instance, here might be the motor with the motor shaft, and then we would have some sort of coupler. And then you would have the shaft, and the key here is the pulley. But this shaft over here would have its own bearings. So now these two bearings right here are taking the load. They're designed to take the load. They're taking the load not in single shear. They're not taking it and applying a moment about, let me draw that. They're not applying a moment about these two bearings that are in here. They're actually putting it in double shear. So it's a much stronger way to do things. You don't have it, what we would call, this would be what we would call an overhung load. So that would be the more proper way to do it, but yeah, I know, it's the topic. You can't help it, right? So the trouble is, this is a spring, and you've got another shaft here that's a spring. In fact, part of what I need you to think about here is this is essentially a spring. If you're going to have a flexible element, the belt that's got to go around corners, it's got to be flexible. So this system of belt and pulley is just fraught with, it's a series of springs. Which means that between the motor and the load, you have a number of flexible elements that all have their own stiffness. And I guess you could go look up the individual stiffnesses and try and figure out the transfer function of what's actually going to happen out here at the mass when you move the motor. But you start to lose control when you lose the stiffness. So what you have to do is back off the bandwidth a little bit. And there's really only a few things you can do to keep the stiffness in the system. One solution to get rid of the shaft loading is to offload it this way. Another solution for the shaft loading is to put in a motor and buy a gearhead. And what happens when you do that is all of a sudden when you're doing two things, I mean, you have let me address the other problem is over here is a mismatch of speed and torque. What I mean by that is just naturally if you look at how motors move, motors go 1, 2, 3, 5,000 RPM. Let's see, 3,000 RPM would be 50 revs per second, right? Is that right? Divide by 60. Yeah. So you've got motors that like to spin fast, but in reality, if this pulley had a certain distance of R, and you want this mass to move, I don't know, what would be a decent speed for that mass to move? Like in the concrete extruder thing, it's going to be really slow unless you're going home, and then you might be, I don't know, 10 inches per second, something like that. And when if just for instance, your speed up here, the mass was 10 inches per second, and you had a radius that was large enough when you're designing pulleys, when you're designing both of these pulleys, the things that you've got to think about are transmitting the torque and having an, so you have to have enough grip to transmit the torque, which either means a certain amount of belt surface that comes in contact with the pulley. And you can either do the belt surface in contact with the pulley by a larger pulley or by a wider pulley and a wider belt, which are a little bit more difficult to make. So let's say that we were just even doing a radius of 3 inches. If R is 3 inches, then the circumference is roughly, let's see, pi times diameter. So 6 times 3, 18 inches. No, something's wrong. 2 pi R is the circumference. So R is 3, 6 pi, yeah, about 18 inches, something like that in circumference. So that's a long way. That means 10 inches per second. I was trying to get it down to 10 so that it'd be easier for you to see this. Let's say R is 2. Let's say R is equal to roughly 2 inches. So the diameter is 4 times 3. So the circumference is about 12 inches. Thus, your speed of the motor, the rotary speed of the motor, inches per rev, that would be. So the speed of the motor would be 10 inches per second times 12, inches per rev, 10 inches per second. Nope, divided by 12 inches per rev. And there we get roughly about 0.8 revs per second. That's less than 1 rev per second, and you're flying along out here with the mass at a foot per second. So you can see there's just a total mismatch, and the answer to this is, answer to both of these is, we have a belt and pulley system. You pretty much are guaranteed you need gearing. You need gearing to get rid of the mismatch of speed and torque. You need gearing because it gets rid of the shaft loading issue, because in this gear head, there is a monster bearing on the output of the gear head to handle holding the gears at exact location to each other. So it's much harder to do that than it is to make a motor spin on its bearings. And so gear heads have big bearings generally associated with them. And all of a sudden the side loads, now you can go ahead and put a pulley on the side of this and ask for force out of that, and it can handle side load forces. Make sense? So generally the rule, I could just start out, say, oh, you have a belt and pulley system, buy a gear head. That's what you're going to do. Any other things in general? One of the things that we're looking at here, the belt type. If you are doing motion control, you're going to be looking at a timing belt. And you're not probably going to look at just any timing belt. You're going to look at timing belt that is probably Kevlar or steel reinforced. They put little bands. Forced. I ran out of room. Forced. They put little bands on the longitudinal direction of the belt, give it a much higher spring constant so that it doesn't stretch, and that makes it a lot more useful in motion control systems. As we get into the motor sizing and the fact that you're trying to make a mass move back and forth, but you really only have control of the motor, the springs in a belt and pulley system, especially given how long this spring is that's in tension, it's got to go clear to there. That spring distance to pull it around can be, you know, worst case is when the mass is over here and you're pulling it, you have a spring, almost the whole belt is in tension. One of the other things that you have to do when you design a belt and pulley system that is important is, oops, I should do this. You've got to figure out some sort of tensioning mechanism. And that means, and keep in mind that tensioning mechanism has to be adjustable over time, because when you tension it the first time, it's probably not going to stay exactly there. It's going to stretch a little bit and then probably remain at that stretch, but it's got to be somewhat of an adjustable tensioning mechanism. The tension in here, you have to have the tension that's in the belt has to be greater than the force that it's going to see, or you're going to get slack in the belt. So when you're starting to deal with how to tension this belt, on one hand, you know, if you do it like when you learn how to adjust a V-groove belt on your alternator, you get out your little crowbar and you pull it tight and crank it down, and there, that's tension. But that's not exactly what the kind of forces that you want to introduce into the bearings of this. You actually want it to just be tensioned above the amount of force that's going to be translated, so that you don't get, when you actually do this motion here, you know, move it that direction, this part of the belt is not slack. There's still a tiny bit of tension in it. You don't need much, but you need some tension so it doesn't go slack. That's your, and beyond that is just extra loading of the bearings for the most part. So, and then thinking about the forces, that's something that you would have to kind of calculate. That's going to change, depend on your acceleration, the mass, vertical. It's a design consideration, I guess is what you'd say. So, but how do you tension a belt like that? Well, something's got to move, right? And a lot of times you think, oh, let's put the motor on a couple, you know, I just adjusted the tension on my bandsaw the other day, and I had a little V-belt and a bolt, and I kind of shoved it out to the end and did what I said, cranked it down a little bit. It's like, oh, that'll work. You know, it might slip a little bit, but that'll work. That's good enough tension. And that's not what you're after here. If a belt slips, that is lost motion. And the next movement, if the belt slips in one direction, the next time you go the other way, if you think you have the full travel and that it's in the right spot, you're probably going to hit the end. So you don't just put the motor on a couple of T-slots and slide it down until it's, you generally are going to buy a one-piece belt, and you're going to probably bring those two pieces of belt together. Somewhere out here is where they tend to meet. And somewhere out there is when you make some sort of tensioning mechanism. The best kind are where you can actually loosen a couple lock nuts, tighten it down on a little lead screw type of mechanism. So you've got a mechanical advantage and you've got control over the distance. And, you know, there's lots of different ways to look up tensioning a belt. There's lots of different mechanisms that are you could come up with. But just to pull it in place and clamp it down isn't generally what you're after. One of the other things that's bad that people tend to want to do is they tend to want to tension this belt. They would say, you know what, let's make this belt go up here like this, and let's go ahead and put some sort of, I'm just going to draw it very simply. We're going to put some sort of tensioning idler pulley in here. And that idler pulley will take care of that'll keep the belt in constant tension. Do you see the design element I just put in there though? You know, the spring. That's bad.
Right.
You just can't do that in a motion system. So it's good for V-belts, and V-belts are for transferring power. You run something and you really don't care if it slips a tiny bit. You really don't care as long as it's going about the right speed and getting some torque transferred. There's lots of loads that you use that kind, running your air conditioner pump, running any place you've got conveyors and augers, and you just need to transfer power, but yet you've got that linear to rotary conversion problem. Put some V-belt. In fact, put a couple of V-belts on there. I bought a chipper shredder the other day, and it has a Briggs & Stratton engine in it that always turns, and then it has a kind of a clutch mechanism with 2 V-belts, and you just kind of crank it down and put an idler in, and it belt grabs, and it's now turning the chipper shredder. That's great. There's no control needed. There's no positioning, and there's no velocity control. So it works, but it's bad for motion control because it adds springiness into. Okay, so don't do that. Okay, let's see. Next up would be a similar version of that, which would be there you go. Rack and pinion. So rack and pinion, similar to the belt and pulley, is good for long distances of travel. It's good for high speeds. That's the kind of the keys that with the belt and pulley. Obviously, you're not going to have a lot of positioning accuracy with a long springy timing belt. In fact, if you go look up specifications from manufacturers who sell belt and pulley stages, the complete assembly where they've designed the whole thing, and you go to look up what's the accuracy, the positioning accuracy of a belt and pulley, they won't ever list one because they can't really promise that it's going to stay in some particular range because it's going to change over time. So the best thing that they'll do is give you a repeatability number, meaning during this particular phase of operation, if you do the same thing over and over, it will get to approximately the same spot. I'll cover those terms in a minute. But there isn't even an accuracy specification for belts and pulleys, unlike ball screws. Okay, rack and pinion. In this case, we're going to buy a little rack that has. Oops, it just went away. That's what it did. Put it back. Come back. There we go. This little rack, you're generally going to have some sort of gear tooth. You buy this, and this is all about gear tooth engagement. And you're going to have, do I want to draw a whole gear? No, I'm just going to draw a round gear, but obviously this has teeth on the gear and the trick is I didn't leave enough room. Hold on a second. I'm going to make some more room. There we go. Rack, pinion. I'm just going to draw this one right off the bat with a motor and a gear head. Same issues of side loading the bearing, same issues of tensioning. You've got to engage the 2 teeth, yet neither surface is perfect. You have the same exact issue of the motor speed and torque and what operational point they're in. And again, this motor is turning very slow. The load pinion is turning slow, but the motor is turning very fast. So they're mismatched. So all the same things, very similar motor sizing. Its advantage in this case is that instead of a belt, you now have this tooth structure that's in here. You actually have a tooth engagement. You have a surface to push against. So the stiffness of a rack and pinion is much better. The stiffness went up, but the downside of this whole mechanism is in the belt drive, you had the mass moving along the bearings and that was good enough. In this case, what this gets mounted to, this surface that the rack gets mounted to, has to be fairly flat. Because if the teeth are going to engage, this distance right here, from here to here, has to stay fairly consistent in gearing. If you get it too far in, the gears bind. If you get it too far out, then you get backlash. So you've got all the problems of making your own gears with the rack and pinion. It's up to you, the user, to get this rack engaged and get it just at the right height the whole way. So if this surface here is flat, this surface essentially here has to be the same. It can't be doing this, or you're going to have changing backlash and changing engagement of the gears. So you're kind of designing an open frame gearing system. And so now you're back to, all right, well, let's spring load this tooth down into with a certain amount of engagement force. And that way, if it rides up, well, hopefully you saw the problem already. I just talked about spring loading something in motion control, and you've started to lose your specifications and bandwidth. But again, long distances, as long as you want to buy a rack, you can run the motor back and forth. And when you're doing your motor sizing, the one disadvantage of this is you're carrying the motor with you. And the biggest disadvantage, you think, oh boy, there's the problems of this, I guess. The problems are you're carrying the motor. That's really not a problem. The mass of the motor is generally not that significant to whatever you're doing. The problem with carrying the motor is cabling. The motor needs big cables, and the cables have to flex. They're big, and they need to flex. So all of a sudden now you've got a wiring loom, and you're buying really expensive high flex cables to do this application if it's going back and forth. So this is where you start thinking about putting on a smart motor, and then, but you still have to carry, no matter what, you have to somehow carry the power to a moving motor. So that's kind of the big problem with rack and pinion.
How much would price go up when you go to like high flex cables?
You'll fall out of your chair at how expensive they are. They're like, let's just give you a for instance. Let's say this is a let's say this cable, this motor, it's 1 horsepower, roughly. About 1 horsepower motor out there. So, and if we were to look at those cables for a 1 horsepower motor, now stepper motor is a little easier because you only run it open loop, but most of the time you don't do rack and pinion with steppers, you do it with servos, which means you have 2 cables. One is the feedback cable and one is the power cable, and they run in separate things. I would say that the cable set, let's say you had a 10-foot, 1 horsepower, 10-foot travel. I'd say those cables would be about $800 would be my guess for a set of high flex cables that are going to work in that. It's more than a motor. But I've done systems that are like on movie sets where they want to move a camera back and forth, and they want to have the same exact motion of the camera, so they can have overlays, fake overlays, kind of fake you out. with what's in the camera and what's not. And so they can, if they run the camera the exact same motion, you can't pick up that it filmed two people doing different things. They just overlay it. And those are 20 or 30 foot long rack and pinions, and they need, it turns out the human eye will pick, if they don't do it right, the human eye will pick up that something's not right about those two things. So it's got to be pretty good. One of the things that can happen, sometimes you will find on rotary loads, just as an aside on rack and pinion, let's say that you had a large diameter and load that you wanted to move. Let's say this was 2 feet, some large diameter thing that you needed to rotate. Okay. One of the senior projects is doing something like this with that gaming one where they're trying to simulate the action in a couple different dimensions. So they have a large, there's basically, from the top view here, you can either do a belt and pulley system where you wrap a pulley around it. You're pretty much not going to direct drive it. That's going to be too expensive. Or you can move the over here, and you can buy a circular rack and then run it with the rack and pinion in rotary. So they make such a thing. You can also do things like, I'll draw this in a different one. You could have the belt do something like this, where you wrap it around the motor. The problem with this is your engagement gets fairly limited on the pulley. So you can put a couple pulleys here, and then the belt, essentially goes around like that when you turn the motor. So there's different ways to handle large loads like that other than just direct drive them. But every one of these different designs has a little bit of its goods and bads, and eventually you kind of work through some sort of trade-off until you figure out the one that has the least problems. There's a couple other cams is another, the other way of linear motion. We're starting to get away from motion control because with the cams, you get rotary to linear conversion. So I need to mention it. And typically what you would do is, like, if I wanted some custom motion, I would design, this is a cam. It's gonna rotate about this point. And you would have some sort of cam. This would be called a cam follower bearing. And it would be, unfortunately, it would need to be spring loaded. So what happens then is you can get linear motion. The motion you get is here. It's linear motion that changes according to the radius of this. So as you turn the motor, in this case, I would say this, here's our motor. You're going to get some predictable motion out here that you can design the profile of that motion depending on whether it's a low radius here or the longer radius, and thus you get linear motion out here. This is cams in your camshaft in your engine. This is you have springs that hold it down, and then in the end you're trying to get some little teeny motion that happens at a particular time, and you adjust and buy different cams to make that happen for your engine. So the cam forward, it's linear motion. The advantage of this is it's generally quite high speed, and the stronger your spring, the more this bearing will track the surface as this spin. Now I drew a random cam there that's going to be probably a little bit more lobe-like, more egg-shaped than what I drew, but can give you high speed, but it's also pretty much fixed motion. And your only ability with motion control, you can adjust a little bit of phasing If you can adjust the motor, you can adjust the phasing, but not generally the distance of travel. So, but anytime you need a lot of force and a really high speed, and you want high efficiency, this is going to, you think about the efficiency, you've got rolling and rolling friction. Everything else we've done is some sort of sliding type of thing. So the efficiency is really high. You get a similar thing that just like there's the camshaft in your engine, which operates like this. And then you have a different kind of arrangement where you have the crankshaft, where if you did something on this one where you actually pinned something here and ran a shaft like this and constrained this to some travel with a bearing in an engine, this would be the cylinder, and the constraint is friction of the rings. More often than not, you generally like to have some sort of linear bearing in this area rather than just friction fit. But obviously friction fit works for a long time until it finally wears out. And so in this case, when you turn the motor, now you would have this point here moving back and forth in a longer travel. So this would be a long, kind of a crankshaft type of thing. Both of these are difficult to motor size. And the reason is non-constant acceleration. The way I motor size these most often when I have to, first I would generally kind of hunt and peck and guess at it and oversize it. But if you really had to get down and pick numbers, I would start with a graph of the cam profile and then look at the slope, which would tell you the velocity of what's happening. And then I would take that graph and look at the slope, basically differentiate it again. And you could either do it formulaically, which would be hard because you don't really know the cam profile. You don't have a formula that relates position of the motor to the position of the cam that's probably any normal formula. So I tend to graph it out and say where is one motor versus the other, then what's the velocity profile, and then from there you can get the acceleration profile, and then you look for worst case acceleration and you size around worst case, and everything else is easier. So it's a way to do motion. It's worth mentioning. It has some problems, but obviously it has some really good uses, especially when you have fixed motion that you're going to do the same thing over and over and over. This could be a good solution. It's actually fairly inexpensive. Other than making the cam itself, this motion doesn't have a lot of expensive parts to it, and it's very, very stiff. So it's a pretty high bandwidth system once you make the cam itself. And if you want to change your motion, you change the cam. You have a changeover. So later on in the semester, we're going to do one of these, except we are going to do electronic camming. So stay tuned for that. There's a way around this with software that you can do.